Okay, let's talk about the other types of boundary conditions that you're likely to encounter in COMSOL. First and foremost is going to be the insulation boundary condition. And this is probably the most common that you're going to encounter. Let's consider a diffusive problem. You have something that's diffusing through our domain. You reach a boundary and all of a sudden it can't escape. So you have j is equal to 0. Okay, now be a little bit careful because of the way that j is defined. As we found in last lecture, we saw that j was equal to your diffusion coefficient times a gradient of something, maybe it's concentration, maybe it's chemical potential, right? But then you have these other advective terms, right? You have alpha times c, and you might also have some other kind of term like beta. It is this which is equal to 0, not necessarily the slope. So it's very common, especially with diffusive problems, that the slope is going to be equal to 0 at the boundary if you have insulation, but it's not required. Okay, and later on in the year, if we get into what I would consider to be multiphysics, which is something like Seebeck coefficients, Peltier, Duforce, array effects, we might see that even in diffusive problems, you wouldn't normally expect the slope to necessarily be equal to 0. But nonetheless, insulation is pretty obvious, it's pretty intuitive, and it's very, very common. Okay. Now, the next condition is symmetry. We already started to see symmetry a little bit, but the idea is that across some axis in your domain, it is the same on both sides. But what that means is that you have some kind of a profile on one side, some kind of a profile on the other side, and at this point, the point of symmetry, right, if you did have j, then you would have to have negative j going on the other side. Right? And because it's a point, the two have to be the same. So under what condition is j equal to negative j? The only possibility is if both are 0, right? J is equal to 0, now j is equal to negative j. So whenever you have a symmetry, what you're going to actually be doing is basically insulation. It comes back to insulation again, which is kind of a nice property. Okay? And in the tutorial for Wednesday, let me just bring it up. We actually have two planes of this. Here we have this dashed line when we're looking at the chicken nugget or the chicken patty, excuse me. We have this dashed line, which is denoting that we have cylindrical symmetry. This is our axis of symmetry, and lo and behold, COMSOL has the nice nodes already implemented, axial symmetry. We also have a mirror symmetry on the bottom because we've cut our patty into half. And that's going to be insulation because that's the appropriate one there. It's not an axis of symmetry. Okay, let me go back to my whiteboard. Now, next one is going to be periodicity. Periodicity kind of looks like symmetry, and it is actually a type of symmetry, but it's a displaced symmetry. So for periodicity, what you would have is some kind of profile that looks like this. Not very surprising. And the idea is that this cell repeats. So it would go something like this, such that the value here is basically mapped over to here. But if you do have a solution that has this periodic wavy motion, there's no point to actually calculating the whole thing if you already know what the unit cell is. So you put that into your periodicity. It's a bit more complicated to implement because it implies mapping from different spatial positions from here over to here. Fortunately for you, COMSOL's got you handled. It is actually a Dirichlet condition because you've actually fixed the temperature or your concentration or your field of interest over here to over here. But again, it's very easy. Okay. The next one is a very pragmatic one, and that one is called the generalized boundary condition. Okay, and the idea is this. Say at a boundary, you had your temperature, right? You know what your temperature is, T is equal to T. And you know that out in the ambient conditions, you have temperature T naught. Okay, now, if T is equal to T naught, then you would expect your flux to be 0. And I hope that makes sense. If you have thermodynamic equilibrium, you're not going to have transport. This is the 0th law of thermodynamics. Okay. Now, when T is not equal to T naught, then J is something. Okay. The easiest way to represent this is lines, because lines are easier. Linearity is very easy. So what you would say is that your flux at this boundary is proportional to, not equal to, proportional to T minus T naught. And what that would mean, excuse me, pen's flying all over the place, is that when T is greater than T naught, i.e. the surface is hot, you're going to get a heat flux away from the surface. When it's colder than the outside, then the heat is going to go into the surface, right? Very pragmatic. And then you just put in a proportionality constant, you say T minus T naught, and lo and behold, you have got your pragmatic generalized boundary condition. Sorry, this should be in contact, like that. Okay, and this is actually also in the tutorial. This is the flux over here, right? So this is for the mass transport that's evaporating into the microwave, I guess, in this case. And what we've done is we've implemented this condition. We've put, this is the normal, n is normal, of the flux, J, is equal to this proportionality constant, K, right? You can call it mass transfer coefficient, heat transfer coefficient, whatever you want, and then C minus C, whatever the ambient is. Okay, and you put that all around there, there's your variables. We also have it for heat flux, right? This is convective heat flux. Again, we can see the equation, n dot q is equal to q naught. I don't know why they put this in separate things, but then they have the exact same expression there. Okay, now, since we spoke about the idea of this conjugate heat transport and using multiphysics to nail these things down, you might be thinking, well, maybe we should actually be doing fluid dynamics in there, and that would give us a more precise answer. But the engineering, we've all got the rings, or maybe you guys don't actually at this point. The engineering side to that is even if you are modeling fluid flow in your domain, there's still a lot of uncertainties that go along with that, right? What are your material properties? What are your uncertainties on the material properties? Do you have the right boundary conditions? Is it slip? Is it no slip? Do you have turbulence? Do you have convective motion inside the mic? It kind of cascades to the point where actually just saying this pragmatic condition, once you've validated it, right? You test it a few times, you draw your curve, you fit a line because you can always fit a line, and lo and behold, now you have your boundary condition. So yes, it's very simple. Yes, it does kind of fly in the face of a lot of what we're going to be doing in computational multiphysics, but just at the end of the day, do remember that you're not going to get a lot of resistance if you show from the approvals and your managers if you rely on this. Actually, sometimes you're going to get a lot less. Okay. The last thing that I want to talk about, and this is real multiphysics, is sometimes your boundary conditions from one type of physics is going to influence the other ones. So this condition, or this particular problem, is talking about water evaporating from the surface of your chicken patty. Okay, there is mass flux of the water into the atmosphere. There's heat flux because of this convective current, but there's another thing too. When the water is evaporating, it's carrying away its latent heat of vaporization. Okay, and this is where it gets really interesting. And this might be a design project in the future to see which is actually, when you blow on a cup of tea, how are you actually cooling it? Is it convective heat transport or latent heat vaporization? Anyway. Hint, hint. Let's look at the boundary conditions for this one. They've implemented it here. You'll recognize this as the mass flux that was lost here. They've just had to put that out into an explicit equation, right? Kc times Cb minus Ci, right? The current minus the ambient. That is exactly the same as they put here, but now they multiplied it by this IDA. I don't know why they called it IDA. And if you go over to the parameters here, you'll see it is the molar latent heat of vaporization. Okay, so this is really the striking at the heart of the value of multiphysics, that you can these things. And if you do put in Navier-Stokes and your fluid outside of this domain, respecting your boundary conditions, of course, what you're going to see is now you've got your fluid that's tearing away mass, heat, and latent heat of vaporization, and it gets into a very interesting problem. So I'm really excited to go on for that.